All right, now we've got the fifth episode the fifth principle, I should say. It's the sixth episode on this series on the guiding principles of scientific inquiry. This is number 5, all about replication and generalization. Goodness. So replication so the first two principles really cover the question asked and how do you pick the question that's asked, and the theory that you're working with. The second two are all about the method and reasoning, and the last two principles have to do with scrutiny and replication and a lot of the important stuff to make sure that anything is really robust, rigorously done, all this kind of good stuff. So let's read here a little bit on the fifth principle, which is replicate and generalize across studies. Replication and generalization strengthen and clarify the limits of scientific conjectures and theories. By replication, we mean at an elementary level that if one investigator makes a set of observations, another investigator can make a similar set of observations under the same conditions. Replication in this sense comes close to what psychometricians call reliability, a consistency of measurements from one observer to another, from one task to another parallel task, from one occasion to another occasion. Estimates of these different types of reliability can vary when measuring a given construct. For example, in measuring performance of military personnel, multiple observers largely agree on what they observed within tasks. However, enlistees' performance across parallel tasks was quite inconsistent. At somewhat more complex level, replication means the ability to repeat an investigation in more than one setting, from one laboratory to another, or from one field site to another similar field site, and reach similar conclusions. To be sure, replication in the physical sciences, especially with inanimate objects, is more easily achieved than in social science or education. Put another way, the margin of error in social science replication is usually much greater than in physical science replication. The role of contextual factors and the lack of control that characterizes work in the social realm require a more nuanced notion of replication. Nevertheless, the typically large margins of error in social science replications do not preclude their identification. So, replication is actually really, really important, and there's an issue with reproducibility right now. In another video, I talked about this, where it was the issue of reproducibility has come up a lot in that I think it was a shockingly small percentage of scientists were able to reproduce their own work when they were publishing. So replication is actually incredibly important, because if you repeat it over and over and over again and get the same outcome, then that strengthens that as something that we can generally count on as being true and a real representation of the world. And so that's why it becomes incredibly important to be able to take the same method, put it in a different lab somewhere, put it in a different field site somewhere with similar conditions, and if you get the same result or very close to the same result, then yeah, you've got something that's very consistent, replicable, and more support for your hypothesis as you move toward the idea of it being a theory, more support for the theory. In the case of social sciences, yes, that's because of the margin of error that's involved. There's a little bit more leeway. In the case of physical sciences, it's often a lot less leeway, and it depends upon the measurement error of observations on satellite equipment, on things like that. In the case of things like models, like economic models, climate models, and what have you, replication depends upon things like what's the initial conditions of the model provided to the model. Because that's incredibly important. What's the setup of the model? If all of those kinds of things are the same and you repeat a modeling exercise on a different computer, the only difference there should be within machine precision, which is to say, like in the climate modeling world, machine precision, the differences I should get between one thing and another is something like values less than 10 to the minus 6 difference. So those kinds of things are replication in there. You want something that gets you very close to the same result. If you end up putting it in running it in different people, there's a fly. Running it with different people, sorry about that. So replication is incredibly, incredibly important. Much greater than the role of contextual factors and the lack of control that characterizes work in the social realm requires a more nuanced notion of replication. Nevertheless, typically larger margins of error in social science replications do not preclude their identification. And that's true. Larger margins of error there, because that is a notable feature of social science anyway, doesn't mean you haven't replicated something here. So that's the difference between physical and social sciences. Often with physical sciences, we have less margins of error, as I've already said, so that's not as much of an issue. If you do end up with large margin of error in the physical sciences, sometimes it says something, did you replicate a method appropriately? Did you replicate the experiment appropriately? Did you replicate the original research appropriately? Or was there something about the context that you didn't account for? Something from the original study that you didn't account for when you redid the study. And in that case, it might be a really interesting result to realize, oh, hey, maybe this thing doesn't hold up as well as we thought. That's the point there. So replication often takes place in different circumstances. A good example of this, thought I heard something, a good example of changes in replication and what have you, changes in context that affect how replicate things is the earlier example I had with the climate modeling exercise in Puerto Rico versus Hawaii. Same climate model and the same setup. We ended up with two different results in that regard in Puerto Rico, but the difference there is, of course, Puerto Rico is closer to the equator. Hawaii is more mid-latitude than Puerto Rico is, but things like that are differences that matter, actually, so it's not perfectly generalizable in either case. There. Having evidence of replication, an important goal of science is to understand the extent to which findings generalize from one object or person to another, from one setting to another, and so on. To this end, a substantial amount of statistical machinery has been built to help ensure that what is observed in a particular study is representative of a larger interest, i.e. that it will generalize, and to provide a quantitative measure of possible error in generalizing. Non-statistical means of generalization, triangulation, analytic induction, comparative analyses have also developed and applied in genres of research such as ethnography to understand the extent to which findings generalize across time, space, and populations. Subsequent applications, implementations, or trials are often necessary to assure generalizability and clarify its limit. For example, since the Tennessee experiment, additional studies of the effect of class size reduction on student learning have been launched in settings other than Tennessee to assess the extent to which the findings generalize. And this is important. That's the reason, again, for replication, is to see, does it repeat over and over and over and over and over again to get to that sort of general rule about how this process works in the real world that you can generally just say that we're pretty sure it's true. You will keep repeatedly testing over and over and over again to the end of time, because we're looking for the instance where it's false, really, because that's the falsifiability thing as far as Karl Popper is concerned. You're looking for the instance of where it would be false, for sure, so you can refine that theory, refine that hypothesis that you have. But generalization is really important because as you replicate over it, you gain the credibility to the point where you can generalize something in here. And statistical machinery is actually really important to that in looking at multiple results and analyses and making sure also that you get measurement error and uncertainty involved in that. And again, that also connects with confidence in there. If you're repeating a study over and over and over again and claiming the same result, that also improves the confidence in the reasoning behind why something would happen. And therefore makes it more credible. General model of the world kind of thing is what we get to. In the social sciences and education, many generalizations are limited to particular times and particular places. This is because the social world undergoes rapid and often significant change. Social generalizations, as Cronbach puts it, have a shorter half-life than those in the physical world. Campbell and Stanley dubbed the extent to which the treatment condition and participant population of a study mirror the world to which generalization is desired, the external validity of the study. Consider again the Tennessee class size research. It was undertaken in a set of schools that had the desire to participate, the physical facilities to accommodate an increased number of classrooms, and adequate teaching staff. Governor Wilson of California, quote, overgeneralized the Tennessee study, ignoring the specific experimental conditions of will and capacity, and implemented class size reductions in more than 95% of K through 3 grade in the state. Not surprisingly, most researchers studying California have concluded that the Tennessee findings did not generalize to a different time, place, and context. And this is also true, particularly with social science, that is very time, place, context specific, and this is actually a very good point to see where the woke actually failed now that I think about it. A lot of the critical race theory, critical theory stuff ignores progress made since the 1960s, changes in attitudes, changes in a lot of different things. They ignore that context and they make their entire judgment upon what happened in the past, or they say because this thing was founded on something in the past, it is awful now. But they ignore the changes in context that have happened since then here. So their findings of critical theory really don't generalize as well as they think it does there. So that's a point to note on the woke. So that's it. This is probably one of the shorter videos because it is one of the most important things, but it's also very easy to state. It's the idea that if you're doing a study, you want to do it. If you're studying something in particular and you do it over and over again, different times, different places, different areas. Like for me, in a climate science realm, I would test things in this part of the country or in a small part of this part of the country where I am, and then run it off into different parts of the country or test it for the whole country. Does it hold for the whole country? Those kinds of things are replications that I would do with my thing until I can get to the point where I can generalize and say, oh, hey, look at this. It actually works in different parts of the country and different parts of the world. So that's it for the fifth principle. So we're at number 5 now. Look at that. So first principle, significant question that can be empirically tested. Data evidence analysis, what have you. Linking research to relevant theory in here somehow or another. Designing a method by which you are actually answering the question. A very good method by which you're answering the question. Coherent reasoning, explicit coherent reasoning that can be replicated. And of course, replication and generalization itself, being able to repeat a study over and over and over again and hopefully get the same results, particularly if it's in different conditions where, well, not different conditions, but if it's different labs where it's done, different modeling exercises, figuring out how to generalize it across time and space. So that's it for number 5. Almost there. We got the 6th one coming soon. That's it for this video. If you like this video, subscribe to this channel, comment below your thoughts. Let me know if there's something you'd like to see or a video or an article you'd like me to review. I'm happy to do that too. And let's see. Yeah, that's it for now. Until next time, I'm Adrian. Stay curious, my friends.